Okay, so welcome to Lecture 10, the first lecture of Unit 2. So in this lecture we're going to be talking about the orthogonal complement of a subspace. Okay, so this is an idea we've been sort of building up towards in some of the homework and test problems. Okay, so let's let H be a subspace of Rn. Okay. Now we can ask, what are all the vectors that are orthogonal to every vector in H? Okay. Can we find that set of vectors? Okay. So we're going to illustrate this by using an example that continues on from a test question from test 1. Okay. So remember test 1, we had these two vectors, u and v, and we wanted to find a w that's orthogonal to both of them. Okay, so in that question we just wanted one w. Now we're going to ask for all the possible w's that will be orthogonal to these two vectors. Okay, so these two vectors, u and v, okay, we can define the subspace that is their span, right? And we're going to call that H. Okay. So sort of by inspection, we can see that u and v are independent vectors. Okay? So that means that H is a two-dimensional subspace. Okay? So it's going to be a plane through the origin in R3. Okay? And a basis for H is going to be u and v. So our task now is to find all vectors w in R3 such that w is orthogonal to every vector in H. Okay? It turns out it's sufficient to just find all the vectors that are orthogonal to just the basis vectors of H. Okay? The basis defines the plane, right? And the plane is the span of the basis. So we just need to find vectors orthogonal to those bases. Okay. So how do we phrase this question? Okay. So we're looking for a w such that w dot product u and w dot product v are both 0. So we want these two conditions. Okay. And we can rewrite that as u transpose w equals 0 and v transpose w equals 0, right? Remember, I think in the very first lecture, we showed that we can go back and forth between the dot product, like this, and the matrix product, like this. Now, since I have my u and my v are known, and my w is my unknown, I can rewrite these two equations as a matrix equation like this, right? Where the matrix A, the first row is u transpose. So we're taking u and writing it as a row vector, and v transpose, so v written as a row vector, and my unknown vector is going to be the w's. That's what I'm trying to solve for, and we're setting it all equal to 0. Okay, so this is a homogeneous equation here. Okay, so we know how to solve this, right? I fill in for u and I fill in for v, the transposes, right? And then I form the augmented matrix, and then I put that augmented matrix into reduced row echelon form. Okay, so reduced row echelon form is just one operation away from this, so we get this here. So I have pivots in column 1 and column 2, but no pivot in column 3. So w3 is going to be a free variable. Now, I want to write the general solution for w, right? I want to find all the vectors that are orthogonal to H. So I write W, and then I write what I know about W1, W2, and W3. Okay? From the first row, I know that W1 is equal to W3. From the second row, I know that W2 is a negative of W3, and W3 is just equal to itself. Again, since W3 is a free variable, I let it be any real number here. And then I factor out W3 from this vector, and I get this vector here. So this vector, 1, -1, and 1, is going to span the set of vectors that's orthogonal to H. Okay, so set of all vectors orthogonal to H is spanned by this vector here. Okay, so notice what we were doing is, this is a null space calculation, right? This matrix A, an unknown, equal to 0, right? So we're computing the null space of this matrix here when computing the vectors that are orthogonal to them. Okay, so we're going to denote H perpendicular, or H perp, as the span of W, okay, to be the orthogonal complement of H. Okay, so let's see what that looks like in a picture. Okay, so the plane here, so this is an R3, right? The plane here is the span of U and V. It's U and V, and that's going to be H, our subspace. Okay. And we're trying to compute its orthogonal complement, H perpendicular. Okay. And we computed that this W, this 1, -1, 1, this W will be perpendicular to every single vector in the plane. Okay, and further, every vector in the span of W is going to be perpendicular to every vector in the plane. Okay, and those are all the vectors that will be perpendicular to H. Okay. Okay, so now we're going to state some definitions and generalize what we did up here. Okay, so let's start with a subspace W of Rn. Okay, we're going to define the orthogonal complement of W to be the subspace W perpendicular, or W perp, to contain all the vectors in Rn which are orthogonal to W. Okay, that's the definition of the orthogonal complement. Okay, so the way to compute it in general is the same way we computed it for this example up here. Okay, so let's suppose we have a subspace W. Okay, and since it's a subspace, it has some basis. Okay, right? Every subspace has a basis, okay? With the exception of the zero subspace. Okay? Every non-zero subspace has a basis that you can just write. Okay? So to compute W perpendicular, we're going to form the matrix A, where we set the basis vectors equal to the rows of A, like that, just as we did in the example. Okay. Now, to compute W perp, we solve for the homogeneous equation AX equals 0. Okay. In other words, what this is saying is that W perp is the null space of the matrix A, where A is formed by setting the basis of W to the rows of A, right? And notice this statement also proves that W perpendicular is in fact a subspace, right? Because the null space of a matrix is always a subspace. Right? Okay, so right, this is the exact method we used to compute H perpendicular in our example, right? We had our H and we had its basis UV. So we formed our A matrix by putting its bases as rows and then computing the general solution. And we got a spanning vector for the general solution. In other words, the basis of the null space of this matrix, right? And that vector spanned H perpendicular. Okay? So we could have done it the other way around. Okay, we could have started with H perpendicular and then asked what are all the vectors perpendicular to the span of W here. Okay, and we do the exact same method to find this plane. Okay, right? We would form a matrix A, which just had W as a row, okay? And then we would solve the system. We would solve the null space of this vector set to a row. And then what we would get is the null space of that would be spanned by this. So you might want to try that as an exercise. Do it the other way around and it'll still work. Okay, so let's discuss some properties of the orthogonal complement. So if W is a p-dimensional subspace of Rn, then its complement, W perpendicular, is a n minus p dimensional subspace of Rn. Okay, so we saw that in the example, right? We had our W at first was a plane, dimension 2, and its complement was a line. So 3 minus 2, a dimension 1 subspace. Okay, and so proving this is a straightforward thing, basically invoking the rank nullity theorem and looking at how you compute the basis of a null space. So that's a good exercise to prove this. Okay. And along with that, we know that the dimension of W plus the dimension of W perpendicular is equal to n, the dimension of the space that they're in. Okay, so this fact goes along with the first fact. Now we have the fact here that if I consider the sort of perpendicular operator, and I do it twice, it cancels out. Okay, so this makes sense, right? If I have a space W and then I consider all the vectors perpendicular to it, I get a subspace. And then if I ask what are all the vectors perpendicular to that, I get the subspace back. Okay, so subspaces are mutually perpendicular in that sense, or mutually orthogonal. Okay, and another fact is that W and its complement, okay, orthogonal complement, the intersection, okay, so the intersection is the elements they have in common, or where they meet, is always only going to be just the zero vector. Okay, and we saw it in the diagram of the previous example, right? The line intersected the plane at just one point, the zero vector. Okay. And there was a test question that essentially asked you to prove this, right? In the test question, we said if x is in the span of a line, and x is also in the span of the plane, that's the orthogonal complement to it, you needed to prove that it forced that x is a zero vector. Okay, and the way you prove that is that since x is in both of these, that means x is orthogonal to itself. So x dot x is 0, therefore the length of x is 0, therefore it's the 0 vector. Okay. And this last fact is about the complements of Rn in the 0 vector. Okay. Remember, Rn and the 0 vector are subspaces of Rn, and they are the orthogonal complements to each other. Okay, so Rn and 0 are sort of the two extreme subspaces, right? Dimension n and dimension 0. So if you think about it, it makes sense, right? If you think about Rn and you asked what vectors are orthogonal to every single vector in Rn, the answer is just the 0 vector, right? It's the only one that will work. The other way around, if you have the 0 vector and you ask what vectors are orthogonal to the 0 vector, and it's the whole space. Okay. Okay, so now I'll mention a theorem that you actually proved in one of your assignment questions. Okay, so if I let A be an m by n matrix, then we know that the row space of A and the null space of A are subspaces of Rn. Okay. Further, we know that these two spaces are orthogonal complements. Okay, that is row space perpendicular is equal to the null space. Right? Every vector in the row space is orthogonal to every vector in the null space, and vice versa. Okay? And that's a thing we proved in assignment 2, question 5. Okay. The final property of orthogonal complements I want to discuss is what's called the direct sum property. Okay, so let's consider W and its complement W perpendicular, both subspaces of Rn. Okay, now we say that Rn is the direct sum of W and W perpendicular, and we write it like this. Rn equals W, and then plus with a circle around it, W perpendicular. Okay. So what does it mean to be the direct sum? Okay, so this is a nice property. Since these two subspaces are the direct sum, Rn is the direct sum of these two subspaces, that means for every x in Rn, okay, we have a unique way of writing it as a sum of a vector in W and a vector in W perpendicular. Okay, and so x equals a vector in W and a vector in W perpendicular. And these two can be chosen uniquely. Okay, so it might help to look at a diagram to see what this is saying. Okay, so let's pretend W is the plane, okay, and W perpendicular is the line that goes through it like this. Okay, so what this is saying is that if I just choose an x in Rn, so let's just say this vector here, okay, it's saying that there's a vector in W, okay, xw down here, and a vector in xw perpendicular, so this vector here, okay, such that when I add them together, they equal x. Yeah, you can see that this vector plus this vector will equal x. And there's a unique way to choose these two vectors. Okay, so this drawing might be familiar from first year linear algebra, because what these vectors are the projections of x onto these two subspaces. Okay, so x projected down onto w is going to be this xw here, and then x projected over to w perpendicular is going to be this x w perpendicular here. Okay. And so orthogonal projections will be our next topic.